Hey adventurers, welcome back. And today we are at day 16 on our journey of Advent of Code 2024. We are on a spoiler-free discussion journey from last 15 days and we have had tons of fun. And since it's day 16 today, I'm presenting you from a hexadecagon camera. And did you know that hexadecagon is also called hexakidecagon? Try saying that 5 times. If you are new here, I am Jatin Kumar Malik. I am a principal engineer who absolutely loves solving these problems every year. Last year, I did a whole blog post series on Medium, and this year, I'm doing YouTube. Check out my playlist for day 1 to day 15 discussions, where we took a deep dive into problems behind the scenes and understood how we can solve the puzzles. And we also got to learn a ton of new things. So, without further ado, let's get started. So, today, our day 16 is called Reindeer Maze. And let's read it. It's time again for the Reindeer Olympics. This year, the big event is the Reindeer Maze, where the reindeer compete for the lowest score. So there is some kind of a maze. Oh man, we have been just on 2D puzzles from last few days now. Yesterday also we had really fun solving a warehouse puzzle where the robots were lost and we tried to find how their patterns are. But let's see what today holds in the score. And in this maze, we have to find the lowest score. So I like writing things down as I read the puzzles, help me build the context, and then we have all the requirements like in one place. So you and historians arrive to search for the chief right as the event is about to start. It wouldn't hurt to watch a little, right? And if you are new here, this is a reference to the chief historian who is lost since episode 1. Check it out, and we are following the same storyline. I have been trying to help the elves to find the chief historian, but we haven't made much progress, and we really need to find him so that we can save some Christmas. And let's read on. The reindeers start on the start tile marked S. So the starting position is marked as S. And they facing east. So they start facing east. And need to reach the end tile marked as E. So we have an end tile marked as E. And the reindeer has to go from start to end. Fair enough. They can move forward one tile at a time, increasing their score by 1 point. But never into the wall. So we have similar where we are given a hash or a pound sign which represents a wall. And whenever reindeer moves, so one move is equal to 1 point. Okay. They can also rotate clockwise or counterclockwise 90 degrees at a time, increasing their score by 1000 points. So whenever you do a common move in the same direction, you get 1 move per point. But whenever you do a rotation, and rotation is expensive, especially at a 90-degree angle, you have a score of 1000 points. And here point is more like a penalty because we have to find the lowest score. But okay, that's an interesting detail. And rotation can happen either clockwise or anti-clockwise. So that's fine, clockwise and anti-clockwise. So to figure out the best place to sit, you start by grabbing a map, your puzzle input from a nearby kiosk. For example, so we are given a map here. Let me get this in our whiteboard so that it's easier for us to do some dry run. Okay, so that's our example given here. And there are many paths through the maze, but taking any of the best path would incur a score of only 7036. And then they have given us how we can achieve that. But let's first locate like what are we given in this. So we can see that our reindeer starting position is here and the ending position is here. And it's simple pathfinding question where we have to find a path through the maze to reach the end. The interesting thing to remember here is that we are starting facing east and we have to try to minimize the points. So yeah, let's see. Initially, if you have to see the path, and if I try to reduce the opacity and see, we are starting facing east, but it's very clear that we cannot go anywhere because the path gets blocked very soon. So it seems like we will take a path like this, and then we will be given some choices. So it seems like we will explore some of the paths to go to the E position. So this is one of the paths that I can just quickly draw and see. The second path seems like you can just keep going straight, keep coming here, come here, and you go here and you go here, and then you can go to the east part. And there can be multiple paths and multiple variations. So if you see here, like you could have turned here and then followed the same path. And then if I had to see one more variation, it seems like to reach this point, we have one more way where we can go from here, go here, come back, and then join the same path towards finding the endpoint. But one of the interesting part that it says is that the best path. So what do we mean by best path? So the best path is the path that will give us the lowest score. And what is the lowest score here? The lowest score that is given to us is 7036. And they have given us like the path that is the best one, which involves going 36 times in a direction and turning 7 times 90 degrees. So plus 7 into 1000, because we have a penalty of 1000 every time we turn, giving us a total of 7036. And here they have given us like what is the best possible path. So it seems like it's the path that we drew from our red line here, where it is going like this, going down and going up. And the idea is like whenever you turn, you have a cost of 1000 points that you have to pay. And then whenever you are going in the same direction straight forward, you just incur the cost of 1 point. And one important thing to note here is that we always start facing east. So here there is a hidden 1000 points, which is not shown, but that is one of the interesting edge cases you have to remember that we have to pay here. And then we are given similarly a second example. So I'm not going to draw it, but we can just quickly do a dry run here, where they have given that the best path will cost us around 11,048 points. And one of such path would be this path, where it is going like this, and then it is reaching the endpoint position, the end. The interesting part to note here is that as we saw that there can be multiple paths to the endpoint, we have to optimize for whichever is the lowest. But there still can be paths that like two or more paths that will have same lowest score. So in that case, it seems like we are not given anything, so it should be fair enough to pick any. But let's see, what do we want to get out of this question? So note that the path shown above includes 190-degree turn as the very first move, rotating the reindeer from facing east to north. Yeah, exactly what I said. Like whenever you are starting and you don't have a way to the path to go directly towards the east, you will have to pay the 90-degree turn as soon as you start, so that you can start going up or down or left based on how the puzzle is created. So now we are given a puzzle input, and you have to analyze your map carefully and find that what is the lowest score the reindeer could possibly get. And if you look at our puzzle input, we are given like a huge maze, and here in the bottom left corner, we are given the starting position, and on the top right, we have the end position where the reindeer has to end. So very interesting problem. Seems like yet another 2D puzzle, but we'll do our best to solve it. But I think now is a good time for you to pause and think about the problem. I have explained the problem. Maybe you should take this, the other example, and try to draw and run some of the possible solutions, right? And then see like how we can ensure that we can find the lowest possible score. And once you are back, we will talk about some of the hints and some of my initial approach that I already can think about. And then we'll take it from there. Yeah, so in case you're looking for hints, let's talk about some of the ways before we jump into the code, that how are we thinking about approaching this problem. So we'll pick up our orange marker and let's talk. So I think one of the initial things that comes to my mind is to think about how you can represent the reindeer's state as it is traversing in this maze. And so let me write it down. So we need to understand that how will we store reindeer's state. So what data structure comes into your mind, and then how will you preserve its states going through the maze? And the question here to ask yourself is like, what information do you need to keep track of as it moves through the maze? And hint, hint, it is the score. So as you're traveling through the maze, I think the things you have to take a charge of is your position, your direction, like which direction are you facing in, and then you need to calculate keep a track of your score. And why keep a track of score initially and why not keep it later? Well, as you traverse through the maze, it will help you eliminate. So once you reach the endpoint, you will have the first base score to start with. And then all you need to do is you need to come back and you need to explore other paths. But what that allows you is that allows you to eliminate all the paths that you don't need to travel, because as soon as you are going on a path and it increases the base score, there is no way it can be the lowest score. So you can abandon that path and you can look at some of the other paths, and maybe you will find some other path which is lower than your base score, and then that gets assigned to your lowest score that you have found. So I think I should just call it like lowest score. So you need to keep a track of lowest score, and then you need to keep a track of your active score that you have, and then you need to do a constant comparison in between. And second thing is, like, how do you calculate this score on the go? So this directly takes me back to my high school computer science, where we had some pathfinding algorithms where you run on a weighted graph and calculate the score. So a couple of them that comes to my mind is one, Dijkstra. I am sure if you are a software engineer or you have studied engineering in any capacity, you have always heard of that. The another one that comes to my mind is A star, which might be overkill for this, but A star is basically an improved version of Dijkstra where it helps us with a greedy path finding. And this is particularly good when you already have coordinates of your destination. And this is why it came to my mind, because in this example, we already know that our E is located into the top right corner. And this can somehow help us optimize the solution a lot more. But probably we won't need it for the part one, because the map is big, but it is not that big and it's fairly constrained, and we should be able to explore all the paths and do that. And yeah, I think the third one is that you have to think about another optimization on top of these two optimization is that your turns are expensive. So whenever you take like a 90-degree turn, it has a penalty of 1,000 points. So as you are traversing through the maze, can you optimize your algorithm to first prioritize not turning? And this has again a similar benefit of how I was talking about doing an early return here, because in this case, what you can do is, like, whenever you have your reindeer is at a path where you have two paths where you can go, you can always prioritize the one that is going in the same direction that you are storing, so that your score can be minimized. And the idea here is to draw the comparison is to first quickly find a solution and then try to find if there is a better solution than that. So, all right. So that's what I am currently thinking. And I think now it's a time for both of us to hit the pause button and then try to solve the puzzle, write some code and find the answer for this part one. And as we do that, I'll be right back and we will probably do a quick retro on our part one. All the best. Hey, welcome back. And as you can see, we have received our first gold star for part one of the puzzle. And I basically followed the exact same thing that I discussed. And to be honest, I did not follow, I just followed Dijkstra. And what I did is I maintained a map called Visited. And I maintained, at every cell when I reached on that cell, I just maintained the score that was there for that. And at the end, I just kept a track of our end position. So our end position in this case was located in some position called X, Y. And whenever I would reach my visited position, I will see the score. And I will just swap it with a lower score with checking like min of our lowest score, comma, the new score that we got. And at the end of it, we had the lowest score, which was the answer of this puzzle. And this was fairly quick, as I said, because there was not a lot of paths, even in the puzzle input. Finding it was fairly simple. So I did not do a lot of optimizations in terms of prioritizing path based on turning and not turning. But I did go through a DFS approach instead of BFS. DFS meaning that I first explored all the paths that are possible in one direction in one position, which basically meant that we had some of this unintentional optimization, but we could have made it better. But I did not do it because I know we would have to do it in part two. Again, I'm trying to do some foreshadowing here. But yeah, with that, I hope you were also able to solve the part one. And what we'll do is we'll move on to the part two. So let's dive into it. So part two says that now that you know what the best paths look like, you can figure out the best spot to sit. Oh, so we had to find a best spot to sit. So it says that every non-wall tile, so Remember, our hash or pound sign represented a wall. And then we have an S position, which was the starting position of reindeer. And we had an E position, which was the end position where we had to reach. And then we had to dot, which was basically the path or an allowed tile where you could go, the reindeer could run. So every non-wall tile is equipped with places to sit along along the edges of the tile. While determining which of these tiles would be the best spot to sit depends on a whole bunch of factors. So if you have to find the best seat, so there are some factors given. And it is saying that the best seats, like all the seats are along the edge of these tiles, not this one, right? All these seats are on the edge of these non-wall tiles. So this one will not qualify, but all the other ones qualify. So how comfortable, a bunch of factors, how comfortable the seats are, how far away the bathrooms are, and whether there is a pillar blocking the view, etc. The most important factor, however, is whether the tile is on one of the best paths through the maze. So I think we are given some of the other factors. I don't think they are important, but I will write them if they are. So the important factor is that the best seat should be on a tile that is on the best path. And remember, the best path is the one that had the lowest score, at least in the part 1, but I hope it doesn't change, but let's read that. If you sit somewhere else, you would miss all the action. So you will need to determine that which tiles are part of any best path through the maze, including the start and end tiles. In the first example, there are 45 tiles marked with 0 that are part of least one of the various best paths through the maze. So remember, I told you there can be multiple paths that have the same lowest score. So they have marked that with O. So O is marked as a tile which is on the best path, which has the lowest score. And in the second example, similarly, there are 64 tiles that are part of at least one of the best paths. So I think one of the most important thing is that you have to find the lowest score, and then you have to find all the paths where S is plural. And then you have to deduplicate the tiles and then find all the numbers of your best seats that are on those paths, which are best paths, which have the lowest score. So this example makes it fairly clear to look at, because if you see, we are starting from here, and when we go here and when we go here, no matter if we take a right and go like this, if you follow my mouse cursor, or go up and then go like this, the score is probably the same. And then when we count the number of tiles, we just mark all of the best path as O, and then we count them as O after deduplicating them. So we will, in both the paths, we are not going to count the common tiles. So now it says that analyze your map further and how many tiles are part of at least one of the best paths through the maze. And now that becomes very, very, very interesting, because we have to find all the number of tiles. But it seems like there should be a way to build on top of our part 1 solution here. But yeah, with that, I think now is a good time for you to pause and think about the problem, that what are some of the initial approach that you can think of, and how would you modify your part 1 solution so that it works for this. And once you're back, we will discuss some of the hints and some of the initial approach that I'm thinking of taking. So see you in a bit. Hey, so yeah, if you're ready to talk about some hints and some approach, let's get our trusty orange marker and let's talk about some of the hints. So I think one of the first hints that comes to my mind is that, remember how we stored the visited states in the part 1, where we were storing the score of each position and what was the best score to reach there? That information is going to be super useful here. But can you think of a way that somehow we can use this to identify the tiles that we need that falls on the best path? That is the crux of the part 2. And I think another interesting thing is that our input is still the same. There is no modifications that. And now we already know the lowest score. That was your answer of part 1, which is the lowest score, which is the our score for the best path. Can you think of a way that how we can use this number in your code now or in a function and use this as an input for part 2 to find if a particular tile is a part of the best path or not? And I think hint 3, this is basically just giving away the answer now. That think about how we efficiently we can check for all possible directions for each tile when we are looking for the best path. We don't want to skip any tile because remember there can be multiple solutions to reach at the same position. And all those seats, basically all those tiles would qualify for like best seats in the maze. And yeah, we don't want to miss any potential best paths. So I hope that helped. And all right, I think it's time to put on your coding caps back on and let's go and write some code. Good luck. And hey, welcome back. As you can see, we have solved and we have another gold star today. And it took me around 20 minutes to repurpose my code from part 1 and add an extension to do that. And let me tell you how I did it in a clever way. So I never got to the A-star algorithm. Probably there is a clever solution there. But I just used my trusty old Dijkstra and modified it slightly to see like what kind of bookkeeping we are doing. So in Dijkstra, what happens is like as you traverse from node to node, you tend to score like what is the score till this node to get here. And you try to keep the minimum score. And then next time when you come to that node and if you have a score that is higher than that score, you just ignore that and you just keep moving on till you reach your the path E. And when you do that, you know like this is the lowest score here. And then next time, whenever you come to this E position from some other path, you just compare that, oh, is this the lowest score? If not, you just ignore it and you keep this. And at the end, like whichever score you have at your end node is the lowest score to get there. So that is exactly what I followed here. But now instead of maintaining a score, I maintained, wait for it, a path. And with a score. And this was a list of path. So the idea was that whenever I would get to a node from a path and I will have that minimum score, it can be through multiple paths. So explaining the same example, if I'm traversing from here to here to here, and then I'm traversing here to here to here to here and then here. So if I'm going like this to here, let's assume this is end and this is start, and then the other node is going like this and going like this. This will probably have the same score because I'm just turning 90-degree ones and then I'm just going straight 1 and 1. But what I did is that every time I'll come to a node, I will just store like what are all the ways, all the paths that we have to get here, and then I will store a score. And in the end, all I had to do was I already, and the interesting part is I limited the scope because this will result into a sample space that is very large. I also added another enhancement where, let's say my answer from part 1 was 10,000. It was not, but let's assume that this was my part 1 answer. I just used it in a clever way that whenever I'm exploring this chain, since there is no negative function where my points are always additive, whenever I would reach to a path or a cell from some path where my score is going above this, I would just abandon that. I would backtrack and I will see if there is any other path that will lead me there. So that reduced my sample space by a lot. And then when I reached the end, I had like a few paths, and then all I had to do was I had to deduplicate them and then count them. So I just put them in a set and then I count like how many unique best path tiles that I have in that set, which resulted into the total number of best seats for me to sit in and enjoy the race. And yeah, this was a really, really fun problem. And I think it helped because whenever I see path finding, the first bell that rings in my head is Dijkstra algorithm. And this was one of these things where if you know the algorithms, it was really easy to solve it. Else, I think you would have to somehow discover a pathfinding algorithm that can keep a score and then minimize the score. Either way, I had really a lot of fun doing this, and this was better than last couple of days because there I just spent like hours debugging my code and writing my code and trying to find the answer for part two. But this one was relatively quicker. And with this, we are at the end of our day 16. We have 1 hour and 17 minutes for the next problem to unlock, and we'll solve when that comes to it. But I hope you had fun solving this. And if you enjoyed, please like, share, and subscribe to my channel. I would love for you to share these videos with some of your friends who you think will enjoy solving these puzzles and probably learn a thing or two. And definitely check out my playlist for the last 15 days. We have had some really interesting discussions and learned a couple of new concepts. But yeah, with that, I'll take your leave and I'll see you for the next day. Take care. Bye-bye.